Okay, this is a video for the second part of chapter 14, and it starts with single displacement reactions and then goes into double displacement reactions. And the first one that we'll start again in class tomorrow is one element replaces another element that's in a compound. So this is single displacement. The key here to remember is that it produces a new compound and a new element. So for example, A plus BC, if A is a metal, it trades places with the metal B, and so AC will combine with B. If A is a nonmetal, it trades places with the nonmetal C, and then we would get BA plus C. So the key to remember in this here is that metals trade places with metals, and nonmetals trade places with nonmetals. So here's another example here in picture form that you can see that might help. And then here's another one showing two people. It says in a single replacement reaction, this girl leaves her guy here for Joe. So she switches partners. Now Joe and Mary are together and Frank is alone. So again, you have to look at the element that's by itself. If it's a metal, it trades places with the metal. If it's a nonmetal, it trades places with the nonmetal. And that's the key that you have to remember here. When we balance equations and things with that, we follow the same four rules that we've done when we did single or synthesis and decomposition. So the more reactive element replaces the less reactive element. And only group 17 nonmetals participate in single replacement reactions. Okay, then on Tuesday we will go over double displacement. And in double displacement or double replacement reactions, this is pretty easy because all that happens here is the ions from the two compounds trade places. So A and C switch partners. So it would be A would go with D and C would go with B. So we just switch the two metals, A and C. So again, we look at our partners dancing again, and the two men change places with one another. Or if you look at here, you have the bumblebee and the butterfly, and the sun and the tree. So the bumblebee and the sun trade places. So the bumblebee is now with the tree, and the sun is with the butterfly. So in double displacement, again, this is what we'll do in class on Tuesday. We have, again, we look at the first element and the third element, and they trade places with one another. So that's section 3. For the quiz, you'll also need to know section 4. And in section 4 here, we're going to talk about some things that we've already talked about, and then some new things also. So energy and the rate of chemical reactions is section 4. Okay, the first one is exothermic reaction, and we'll do a lab on this week. And this is where energy is released in the reaction. So the energy or the heat is given off and would be found in the products. For example, when light's produced in an electrical reaction, and also in thermal energy. So here, as you can see, the reactants have the energy. Energy is released as it goes into the products. So you'll learn more of the chart here when you get to high school. Endothermic is when energy is taken in the reaction. So so if it's taken in, the reactants would have a lot of energy. When the energy is taken in, then there'd be more energy in the products. So energy is taken in here. So photosynthesis would be an example of this. So the other way of thinking of it, exothermic releases heat or gives off energy, and endothermic takes in heat or absorbs the energy so it will feel colder to the touch. Okay, law of conservation of energy is very similar to the law of conservation of mass. This one says that energy cannot be created or destroyed in a chemical reaction, but only change forms. So in other words, energy is transferred from one object to another. If we're talking about energy in like an exothermic reaction, the energy is released, but it was also had to be stored in the chemical bonds in the reactants in the first place. So again, if you could measure all that energy that's in a reaction, you would find out that we have the same amount of energy before the reaction and after the reaction. So if we think of roller coasters, which we'll talk about when we do this law in physics, all that energy is from the top of the first hill, and that energy is just converted from potential to kinetic. So mainly here, just know the law. Okay, rates of reaction. Reactions only take place if reactants collide, and they have to have enough energy for the bonds to break for this to occur. So to get that energy, we have what's called activation energy. And activation energy is the energy needed to start a reaction. In other words, to activate it. So again, the smallest amount of energy needed to start the reaction. Again, lighting a match, we have friction. Saliva in your mouth is the activation energy that starts digestion. So if you take a cracker, as we talked about earlier in the year, chew it up, hold it in your mouth, and hold it in your mouth for 2 or 3 minutes and then swallow, it'll taste like sugar because your saliva in your mouth has already broken down the carbohydrates into sugar. So activation energy could be from like friction or from a spark. So again, the smallest amount of energy needed to start a reaction. Okay, 5 factors, that affect how fast a reaction occurs. Okay, the first one is temperature. That's how, the higher the temperature, the faster the reaction. And again, the lower the temperature, the slower the reaction. If you place a glow stick in warm water, it glows brighter. If you place it in cold water, it doesn't glow as bright. And we'll talk a little bit more about that in class as the week goes on. Concentration. Okay, the higher the concentration, the faster the reaction occurs. In other words, the more particles there are, or the closer the particles are together because it's stronger, then the reaction is going to occur faster. Surface area. Again, we talked about crushing a sugar cube earlier in the year. So the more surface area it has, because the water can come in contact with it in more places, it will react faster. And then 2 new words, inhibitor and catalyst. An inhibitor is something that slows down or stops a reaction. Food preservatives would be a good example of an inhibitor, and your refrigerator would be an inhibitor, and antibiotics like penicillin are inhibitors. In other words, they slow down the reaction. A catalyst, on the other hand, is something that speeds up a reaction, but itself is not changed. In your car, it would be a catalytic converter. The catalytic converter is going to take and absorb or break down the pollutants and change them into carbon dioxide and water. And then another catalyst would be saliva. So the catalyst is there, so it speeds up the reaction and it lowers the activation energy. So in other words, it doesn't need as much energy to get the reaction started. And that is it for chapter 14. You will have a quiz later this week on it. Make sure you know the vocabulary words. Make sure you know the rates of a reaction here, these 5 here. And the biggest thing, again, as always, make sure you know how to balance equations. We will include both synthesis and decomposition on this quiz also.